Welcome everybody to the Noir workshop. I am Maxime. I'm a software engineer slash language designer on the Noir team here at Aztec. And I'll let Joss introduce himself.
I'm on the Noir tooling team, also at Aztec.
So today we're going to give an overview, to start with an overview of Noir, which is our ZK DSL. And then after that, Joss is going to take you guys through kind of a code together example project. I'm going to provide a QR link later to our CLI tool for doing everything, but there was an email that was sent out like right before this session. So if you want to, there's a link to our installation page if you want to get started on that before, like a little earlier. So first we want to ask, why should you as a developer care about Noir? We want to enable developers of any background to easily get started writing ZK circuits. As the line says here, write ZK programs without being a cryptographer. So now the properties of ZK proofs enable us to greatly expand the number of useful applications that we can have. We now can actually have privacy preserving applications that are also very efficient to verify. However, for a while now, writing ZK programs has been quite challenging. A lot of ZK circuits were written using the APIs of a given proving system, and then interacting with that proving system usually required some knowledge of how the ZK proof construction operates, or also the underlying cryptography that makes that ZK proof system possible in the first place. And then if you wanted to switch proving systems, you also had to rewrite your program in that API of the new proving system. And aside from Noir, there has been a lot of development of ZK DSLs to make these programs a little easier to write. However, they are still oftentimes limited in their scope and the proving systems that they support. Our solution to making ZK circuit writing easier is Noir. So what does Noir offer? Noir is our, as I mentioned, our ZK DSL. It is written in Rust and it's fully open source. For our native field data type, which I'll go into detail a bit later about, is based upon the ArcWorks library. But the main benefit that we try and what makes Noir unique is that we aim to be more flexible in our design than other domain-specific languages that are currently out there. Noir compiles down to an intermediate representation that we call the abstract circuit intermediate representation. This IR, we call it the ACER, can be compiled down to a rank 1 constraint system or Planckish languages. Really, any NP complete language this IR can compile down to. You can think of this as being analogous to something like the LLVM IR, but rather than converting down the IR to a machine's specific instruction set architecture, we are converting our IR to the constraint system of a given ZK proof construction. This then enables us to have the decoupling of the backend proof system and the language. We currently have one fully integrated backend. That's the Aztec Berettenberg library that uses TurboPlunk. However, we do have plans for further integrations, such as Groth16, Halo 2. We do have an integration with Marlin. However, there are some missing features still, so I can't call it a full integration. And due to the fact that we have this, our IR allows you to have essentially these proving system optimizations, which essentially means custom gates. And this is, with Noir, we're providing an interface where you can optimize circuits on the proving system layer. So we have these black box functions that we call, like, they're part of our standard library. We call them black box because their implementation is done by the proving system. A few examples of some of our standard library functions are SHA-56, Pedersen, Merkle checks. However, there's many different optimized functions that we support. Noir was started with three main goals in mind: safety, simplicity, and performance. By being more high level, Noir can abstract away much of the cryptographic safety that would otherwise be necessary in a ZK circuit language. The standard library then enables usage of cryptographic primitives with relatively little knowledge of the underlying checks and constraints necessary to keep that ZK circuit safe. And like how Noir is Rust-based, we are also Rust-like in our syntax as well, with some slight adaptations. We try and have common programming constructs within Noir just as you would in any other normal programming language and make them simple to use. You can constrain variables based upon conditions and loops, and you can also constrain on any integer data type as they will all ultimately translate to our native field type. We have flexible code organization so that you can separate your code into modules and external crates, which will enable developers to easily create libraries for Noir programs. However, although Noir is very high level, we do not look to sacrifice performance while adopting these higher level concepts. Noir compiles down to an intermediate representation similar to LOVM before then compiling further down to the Acer. We optimize both this intermediate representation as well as the Acer. And then due to the fact that Noir has this Acer and is backend agnostic, we can also optimize at the proving system layer as well. Optimizing on the proving system layer is what enables us to significantly reduce our circuit size and thus speed up proving time, as we will now have a smaller circuit. I want to take the chance, though, to highlight some more of Noir's more important features that are supported and show you some more of the Noir syntax before we just dive straight into the coding example. First, this right here, I want to show you how you can easily separate your circuit logic into modules. A developer can import functions as you would in any other programming language, such as Rust. And then we also have globals that can be accessed inside multiple functions of a module, as well as function parameters. And then they can also be imported like a function would in the same manner you would expect. It's important to take note, though, that we currently restrict globals to only literals, such as fields or ints. And then there's also array literals in the pipeline. There are plans to possibly enable compile time expressions for globals, but right now they're currently restricted. With an easy to reason about structure, we hope to make it easy for developers to construct libraries for their circuits and organize their projects. As this is the first Noir snippet that I've shown you, I want to take the chance to highlight the field type, as I've already mentioned it a couple times. This is Noir's native data type, which is derived from the proving system. In the case of Aztec's Brandenburg, the field is a 254-bit finite field value from the BN254 curve. And then all of Noir's integer data types will ultimately translate to this field, as they're just field types with range constraints, where we say that it has to be within this size, bit size. So this field type, though, doesn't have to be 254 bits. For example, with Marlin, you can have a field based off of the BLS 381 curve. So, but with Aztec, you can always think about it being 254. Noir also has compound data types, such as arrays, tuples, and structs. In this snippet, I'm highlighting two of these compound types, specifically arrays and tuples. Many of you may immediately already notice what is happening in this snippet. We are generating a Merkle root from a provided hash path and leaf node. This logic can then be used to construct a Merkle inclusion proof circuit in Noir. This method does live within our standard library, and this is why you might see the usage of that crate prefix when I'm importing different functions. If you were to write this in your own Noir crate separate from the standard library, you would have to import using the std prefix rather than the crate prefix, and you're going to see that in some later examples and also the code example. And if you've already not taken note, you can see specifically the usage of tuples in the snippet inside that main if expression in the for loop. And we're using that to set our left and right side of our, like the Merkle nodes that we are going to be compressing to get to the Merkle root. So here's also an example of our structs that enable you to easily group data. These structs can be nested and they can implement public functions on them. We do also have the concept of self, as you can see in this snippet, and this is obviously very beneficial to you as a developer to be able to group data in this way. We support for loops and if statements and also logical and bitwise operators. In this snippet here, I am transforming a field element into a byte array using our standard library 2 bits method. If you look inside the inner for loop of these 2 for loops, you can see how I'm utilizing bit shifts, but also the OR bitwise operator. As I'm using bitwise OR on U8s here, it will act as you expect for bitwise OR. I also support bitwise AND. However, this bitwise OR AND can be used to mock what a logical OR AND operator would perform, except that would be if you're performing it on a U1. Our bool type translates to a U1 type. So if you were to perform a bitwise OR operation on 2 Boolean statements, you can expect it to act as a logical OR operator. And so this is how we currently mock logical OR and AND in Noir. I want to show a bit more of the control flow. So here's a basic quadratic sort written in Noir. You can, as we did in the previous slide, you can see I'm nesting for loops and conditionals. It is then possible to constrain upon values altered inside of conditionals and loops. When specifying constraints directly, a lot of this conditional logic usually is handled in kind of an arithmetic expression, such as a multiplexer. However, we abstract away much of the constraint generation for the developer. So we want to enable you to continue programming as you would expect in a classical ZK programming language, but now you are in a ZK DSL. We also have recently added generics, which are highlighted in this snippet here. There are 2 examples where the generic is defined directly and also where the type is implied. First-class functions are also active work in progress. We don't yet have a trait construct, but once these first-class functions are implemented, it will be possible to mock the functionality of traits using first-class functions, generics, and structs. So just a little warning, Noir is a work in progress. Do expect bugs and do expect some limitations with the language. However, we're proud of where it's at right now and expect constant improvements as we are going to be continuously iterating upon Noir. So now let's get into how we would actually go about writing a Noir program. So typical 3-step process. We have to set up and write our Noir program. And then because we're writing a ZK circuit, we then have to prove and verify that program. So here is Noir's native package manager. This is also the link that was sent out before the workshop. So for whoever wants to follow along, please scan that QR code and follow the instructions for installation. So Nargo is Noir's package manager that is comparable to also Rust's package manager Cargo. Nargo provides also all the necessary tools for proving and verifying your circuit aside from just compilation. And proving and verification, though, will always require the backend proof system. So currently Nargo has to be compiled with an integrated backend system. So we have binaries on that installation page for your respective environment, and you can also compile it from source. However, unless you already have a setup environment, I recommend just using the binaries, as the backend system is a big C++ library, and compiling it from source might not go perfectly for you. So I'm gonna just wait like 2 seconds, let people install it if they can. Give people a couple sec. I see someone posted the link. Thank you for that. And I'm gonna move on right now, but I'm just gonna do a basic setup walkthrough, and then there will be time to get Nargo set up. Once you have Nargo installed, we can make a very basic project. So create a directory where you want your project to live, and then you can if you've followed the instructions correctly, Nargo should then be installed into your path, and so that you can just call Nargo anywhere on your machine. So you should be able to do a Nargo new cast ballot, and this will create a very basic program that'll have a Nargo toml file and a source file containing this main right here that looks like this. Nargo toml is just the packet is a package's manifest file, similar to cargo toml that you would see in Rust or package.json in an npm project if you're unfamiliar with Rust. This is where we specify the compiler version as well as all your dependencies. The standard library is an external dependency, but is automatically added as a dependency. So that's why you're not going to see it listed under the dependencies there. And if you look at the the snippet on the right, I also show an example of how you can import a local Noir crate and use it as a library in your Noir project. We also allow specification of Git dependencies. That would just require, instead of a path, you would have a GitHub URL and a Git tag. And this can be seen, you can see how to do this in the Noir book. So once you are, assuming you're within the Nargo project that you just created, you can then run a Nargo build. And it's gonna look at your like your main.nr and look at the main function and see what inputs and outputs you have. If you look here, you can remember I have two inputs. One of them though has this pub keyword. So all inputs to Noir are going to be private by default, and you just have to use that pub keyword to say, I want the verifier also needs access to this input. So that's why you see when we do this Nargo build, we have an XY in the prover toml, and then just a Y in the verifier toml. So now we're actually then going to prove the execution of our Noir program. This is going to be done by whoever wants to prove something to the other party. So this could be one of the players of a game. This could be someone you touching the finances of a company, or for example, what we're more familiar with, a roll-up sequencer who's rolling up all your programs to submit to Ethereum. So once your prover toml is filled in, because our circuit is just checking that X and Y are not equal, we're going to pick 1 and 2 as our values, and then we're going to run Nargo prove P. P will just be the name of your proof file that gets generated into and spit out into a proof folder. And then now we can actually, now let's verify our proof. So in the examples I talked about earlier, the verifiers would be the other player in the game, an external auditor, or in the case of a rollup sequencer, the smart contract. That's where you're verifying your rollup. However, we can just verify Nargo here. So we're going to do a Nargo verify P. It's going to look into that proofs folder that was created by Nargo prove, and we're going to run and it's going to use that proof to run verification of the program. And then you'll see the verifier toml is also auto-filled for the public input as it can get it from the prover. So one thing to note here though is if you are to change your like X and Y to both be like 1 or both be 2, Nargo won't even let you generate a proof. It'll return like all constraints not satisfied, because that proof is going to return false. You could theoretically get around that and generate a proof yourself, but then if you try and verify that proof that does not fulfill the logic, you're going to get a proof verified false. So you can try that as well right now if you're curious, but it should not let you generate a proof. So just to recap, we have our typical Noir flow of setup, prove, and verify. Setup, you might have noticed it's missing something that you might, if you're familiar with ZK proof systems, we don't have any kind of trusted setup that we were doing. This is because we're using the Noir Brettenberg backend. So the common reference string that we're using for all our proof programs is the same one from the Aztec key generation ceremony all the way back in 2019. So this avoids the need for a trusted setup at the moment. But as we hope to have like Groth 16 integrations and stuff in the future, we will probably enable you to also do a setup through Nargo. Okay, so now I'm gonna take a chance to look at if there's any questions, um, and answer them before. Can you take an array as public input? Yes, you can. Actually, yeah, you can. You can take in an array. You can also, we just recently added, you can also have structs as inputs. However, those structs have to have either just arrays or field or integer types. Is Noir currently using the Aztec backend Rust repo? Yes, that is our current backend. That's the one. We have the Brettenberg crypto library that's written in C++, but we have to do some extra Rust over top to have it interact with Noir correctly. Will enum be supported soon? I don't know the timeline for enums in Noir, but you probably could mock this functionality. Is the field always the same? The field would differ dependent on the proof system. So right now, like with the Aztec backend, it is going to be 200. It's going to be 254 bits, and you can do like operations on it, such as addition, multiplication, addition, division, but you can't compare fields though. The comparison operators aren't going to work because fields aren't necessarily ordered. So you have to have integers where there's those like U64, U32, where you've had put range constraints on your field. Oh well, we have a lot of questions here. There isn't a full documentation of the standard library yet, but there is you can look in the main Noir repo, and there's one of the main folders is the Noir standard lib, and you can look at everything that's supported there. Ignite SRS is the common reference. Yeah.
When you're answering these questions, can you just remember to say the questions? Because for the video after, no one's going to know what the question was.
You're right. Thank you. I think there were so many. I stopped saying them out loud because I was kept.
I think you have 3 more to the top.
Okay, so one of the questions is, what is Ignite SRS? That's the common reference string from Aztec's ceremony all the way back in 2019. It's what we use to. It's our common reference string for all our Noir programs with the Aztec backend. That lets us generate our proving and verification keys. What kind of optimizations do we perform at the IR level? That's a good question. So there's like technically a couple things that get done, because if you think about it, we have the intermediate representation, and then we also have the Acer. So that intermediate representation, we do a lot of the optimizations that you would have in the normal kind of LLVM SSA pass. We have inlining, we do common sub-expression elimination, we do unrolling, loop unrolling, and all that in our SSA pass. And then also with like the Acer, we do some basic optimizations as well, where we simplify some of like the bivariate equations, and we also like remove kind of all coefficients in our equations that might have 0, just so that we can reduce the number of gates that you're going to have in our representation, and then reduce your circuit size. We actually, if you look at our documentation, we have a compilation overview, and you can get the exact details of how we go through the optimizations for the Acer. Are you planning for any security related tools for auditors? That would be awesome. We don't have immediate plans for that at the moment, but that would be nice to have. Any word on IBC recursion via Noir? But IBC recursion, I'm not sure what IBC means, but I'm assuming you just mean proof recursion in Noir. And that's one of the main things we want to add. That's one of the big, that's one of the immediate things hopefully should happen is on the pipeline. All right, I think I've answered a bunch of questions just now, and it would be a good time to move on to the next part of the presentation. But just throw them in, and we're going to take periodic breaks to answer more Q&A questions throughout. All right. I'm going to stop sharing now, and I'm going to let Joss take over.
Alrighty.
Here we go.
That coming through okay?
I can see it.
Cool. All right. So the example we're going to be building together is on a simple quadratic voting app. So first off, what is quadratic voting? You may have come across the concept or a similar form of the concept, say on Gitcoin. They have a quadratic finance there. So we're going to look at it in the context of voting. Here we got 2 ballot cards for a range of candidates. And the idea is that you buy your votes for a particular candidate by spending tokens, but the cost of each successive vote is more expensive. So you see the cost of 1 vote is 1, cost of 2 votes is 4, 3 is 9, etc. So on the right, we've got a ballot being cast by somebody who really wants candidate 5 to win. That's all they care about. So they've just spent all 100 tokens that they're allowed to spend on buying votes for this one candidate. This other person here, they also want candidate 5 to win, but they're willing to put aside some of their tokens to express what compromises they're willing to make. And because they're willing to do that, they have more voting power. The voter is incentivized to consider what compromises they're willing to make. You see, their vote is 80% more powerful than the person who is not willing to consider compromises. So we're going to be building such a system, and because we're building it with Noir, we're going to be able to have the voters hide their different preferences from everybody else, apart from the ballot manager who they're going to submit their ballots to. The ballot manager will be able to see everybody's votes, but they won't be able to censor or modify them because they're going to be summing those ballots via a verifiable zero knowledge proof. So here's a simplified view of the architecture. We got 2 voters here, Alice and Bob. They've both got their ballots, and they're going to feed their ballot into a circuit locally, and that circuit is going to output a commitment, which is going to go onto a smart contract, or doesn't actually have to be a smart contract, could be a peer-to-peer network, something like that. And then they're also going to send their ballot to the ballot manager, and they're going to aggregate all the ballots together and then send a ZKP to the smart contract again, who is going to verify it and say, yep, I can see all of the commitments have gone into this proof, and the result that you've given me must be valid. So again, this is what each circuit does. So we've got a user circuit who is going to enforce the quadratic voting rules. So check that the numbers add up correctly. Expose a commitment, which is going to go onto the smart contract. And then the manager, they're going to take the ballots and sum them together and also prove that all commitments have been incorporated into this summation. And the smart contract is going to validate both of these proofs, or in the case of the users, every single proof submitted by a user, a voter, and it's going to store these commitments to be used later for validation of the summation, the aggregation proof. So in a bit more detail, here we've got a voter's ballot. So they express their preferences, their votes for each candidate. To keep things simple, candidates are just identified as their index in an array. So we've got 0, 1, 2, 3. Also included in the ballot is a secret. Now the secret is important because if you didn't provide a secret, when you come to hash your different votes, the commitment that you output is vulnerable to a brute force attack. It would be pretty trivial to consider what all the different permutations of votes are, hash them all, see what all the different commitments there are that can be produced. So we need this secret ingredient to add some noise here so that the commitments all look unique. And the other thing this circuit's going to have to do is check the constraints. So we've got to check that each of these numbers squared is going to be less than or equal to the token budget. The manager, they're going to take these ballots. They're going to also perform that same hash that the user performed and check that it is consistent with the commitment that was provided publicly earlier, posted on the smart contract. And then at the end, they're going to output the summation. So 4 plus 0, 4, 3 plus 4, 7, etc. So, first exercise. We're going to be looking at the enforcing of the QV rule, which is checking that the sum of the votes squared is less than or equal to the budget. And we want to do this because this is how we know that we're following the rules of the game. In order to write this, we're going to be using a few of Noir's concepts. We're going to be using mutability because we're aggregating a sum. We're going to be looking at a few types. We're going to look at the global type for sizing the arrays, the integers, which are going to be summed together, and the array that we're going to be iterating over, which is going to contain all the votes. You're going to iterate using a for loop, and we're going to be using the constrain keyword. And now this is an important concept, which if you've not written circuit code before, it is new. You won't see this in more traditional programming languages. This is the ingredient which allows you to say this circuit tells you that a certain thing is true. So it looks a bit like an assert statement in other languages, except if you played with Circom, it's different from the assert in Circom, which won't actually affect witness generation. But in the case of Noir, it does. Right, on mutability, this is what declaring a mutable variable looks like. You need the mute keyword. If you don't have that, then reassigning it is going to throw an error. This is what a global looks like. Globals are constant. You don't need to worry about a global getting reassigned and causing confusion later. An unsigned integer has its type constrained using the U followed by the number which specifies the number of bits. So this is an 8-bit integer. And an array, it follows this syntax here of saying what type the element is, and then the number of elements. You can assign it as a literal. There's also another literal assign you can do, which is like the first element is the how you want to initialize every element in the cell, and then you have a semicolon, and then the number of elements. This is what a for loop looks like. So you've got the range operator, which is familiar from Rust. And here's a constrain keyword. So you can just have whatever binary operation you want to use here. So we're going to give you a bit of time to mess about with these concepts. If you go to the docs page, you'll see all of these ideas that we just covered there. And we'll give you a bit of time to check that you can compile a program, assign a variable, do a for loop. And then once we've done that, we'll look at the spec for the first function that we want to implement, and then we'll go on to the implementation. In the meantime, it's probably a good time to take some questions. So in Maxime's part of the presentation, we saw that we can have an array without specifying a length. Is it a feature only available for the main function? Oh, hang on, ... main function parameter. So for the main function, you will always have to specify a length of the array, because when the circuit gets compiled down, it's it has to have fixed length arrays. When you are writing more general purpose functions, you can write an unsized array as your function parameter.
You might have seen it in I think my compute root from leaf function. The hash path is it looks like a variable sized array, but that method is going to be called from a main function. And the main we do have to know the array size. We don't have variable sized arrays from main just yet. So the compiler would then figure out that the array being passed later down to another method that has a variable size parameter, what that array size is. You currently do need to know the index of an array. It has to be compile time.
Got another question. Where do we see Noir a year from now? And what features does the team want to see integrated? So
All right.
I think in the short term, there's a lot of features which just need fully integrating with each other. So we have arrays as inputs, but it'd be great to have arrays of structs. I think that's going to be a great improvement to the language. This is what I'd personally like to see. Other big work we're going to be doing is related to the Aztec free roadmap. At some point, we've got to consider how we want to make the language extendable to consider concepts like private state, getting and setting a private state on contracts, that kind of thing. Note that Noir itself will never be a contract language. That would be an extension to a Noir, which would enable that concept.
Yeah, I think stateful Noir is one of the big things that could be happening a year from now. Some extraneous features like recursion and like proof recursion inside of Noir and other things should hopefully be happening sooner. I think the more exciting stuff is stuff like, yeah, stateful Noir and the extension language for smart private state, like Josh just mentioned.
Yeah, I'm excited for proof recursion. That should enable a lot of new use cases.
Thomas asked, how could you do a tornado cache like proof where you want to prove that a hash is included in a list of all user deposits if your list has to be fixed size? Well, you could do that through that compute root from leaf method. You would just have tornado cache doesn't necessarily have a list of all user deposits. It stores it as a Merkle tree. So if you provide the correct leaf node and you provide the hash path up to the root of that tornado cache contract where the Merkle tree is stored, you can do a tornado cache like proof. Yeah, you could theoretically mock it by having user deposits of a list of a max size of some sort, but you can also do it through a Merkle tree instead, and the hash path will always probably be like depth of 32 or something like that. Take one more question, and then we can maybe move on to the next part.
All right, we've got, is reference type, i.e. ampersand, not implemented yet?
No, it is not. That would be it's a little bit challenging of a thing for a ZK DSL. That would essentially mean we have non-determinism. This is actually very powerful though, and it's something we want to implement, but we have to be careful about it. And we hope to have that eventually, but right now, no.
Cool, I'll move on. So here's the spec for the function we want to write. We're going to be checking this quadratic function. So we are going to be aggregating the square of each of our votes and then checking that that summation is less than or equal to the budget. So our function is going to have two inputs. It's the budget that we're adhering to and all of the votes that we're going to be iterating over, squaring, summing, And then at the end of this function, we're going to be performing this constraint check. So if you haven't already, as Maxime prompted earlier, create a Nargo project, a Noir project using Nargo new. Go in there and open your main file and get coding. And we'll, I think we're going to give you 7 minutes to have a go at implementing that function. In the meantime, we can take any more questions if people want to ask.
Yeah, if you have errors, we can maybe answer them too. Although we're not looking at, it's hard to see what exactly everyone's coding, but yeah. Joss, maybe we go back to the specs. Someone just asked, can you give a link to the specs? Maybe we go back to that page.
Yeah, sure.
Wisdom, you asked, cannot find module. If you installed it using the that's reminiscent of an old error that I'm surprised you're getting. If you installed using the binaries, you should be using it should be installing with a tool that doesn't use the this old WASM based backend we had. You could also try to use the compile from source. You're just going to have to use the WASM executable backend. It's in that installation guide. It's going to be option 2.1. You're going to have to replace the dependency in cargo toml, but that should hopefully solve that.
I'd say it's worth noting if anybody is using an old installation of Nargo, it's worth updating because it changes quickly.
How can you pass in an array as input in the prover toml? So that would be, you would specify it as you would in a list in a toml file normally. You would just have 2 brackets and then your list of numbers. I'm actually gonna drop a link in one moment to our Nargo tests that should have some examples of just some of the different inputs and all that, so you can get a look at it. So here's a link to an array test inside of Noir. You should be able to see in the prover toml there how you would specify an array in the toml file. There's also, from that same link, you can go back into the test data directory. You'll be able to see a bunch more examples where we test Noir.
We have
So
a question. Sorry.
Oh, that was it. No, you got it.
Should we call our function main or check within budget and call it from main? So I would create a new function, check within budget, and you can call it from within main. You don't actually need to call the function in order for the program to compile. At this point, we just want to check that you know how to write the right syntax. But if you want to build and run it, then yeah, you would want to call it from main. Oh, right. Sorry, I did not bother explaining that candidate count is a global. I should have said that. So if you put that at the top of your file and set it to some number like 10 is what we've been using. So you'll have global candidate count equals 10 semicolon, and then you can use it later on in your function signature.
And if you do write a main function that calls check within budget, and you'd also be taking in, yeah, just like that there. You can use that candidate count in both the function signature of your main and then your check within budget function as well.
We'll give you another 3 minutes. We got a question, is Noir suitable to be installed in Ubuntu 18?
It should be. The I recommend just using the binary for this presentation, but you should be able to compile it from source on Ubuntu. Actually, probably easier than on Mac or Linux due to the C++ backend. But I've mainly been working on Ubuntu 20, and some people have done 22, but I don't see why 18 would be a problem.
We have a question. Could we give a sense of what schemes are supported via what backends, and if and where a Solidity verifier is available? And do you have a roadmap that we can use to plan contributions? So at the moment, the only backend that's fully supported is the Berettenberg backend, and there is a command for generating a verify contract for proofs in this proving backend. As for other proving systems, do we have a roadmap? I imagine we'll be putting out grants, perhaps.
We're in discussions with some people who want to integrate backends with regards to someone planning contributions. You can take a look at our GitHub. We have issues, a bunch of issues. We probably should label which ones are better to get started with for the first time, but I would say it's not a roadmap, but it's somewhere to look if you're planning to contribute.
Shouldn't token budget be a field type? So the reason that we're not making it a field type is because of this part of the spec here, laser pointer. We've got a range check here. If it were just a field, you wouldn't be able to do a range check. The concept just doesn't exist for fields. They don't necessarily have an order, but integers do have an order, so we need it to be an integer. Can an integer sum overflow? I'll let you field that one, Maxime.
Yeah, but it will. We do. You can have overflow. Same thing with multiplication and all the other with like operations like that.
Cool, that's time. We'll come back to more questions later. So here's a solution. So global defined as stated. Here's our our function signature. So we've got the token budget, our U32 type, and the array of votes, which is of length candidate count, and all the elements are of type U32. Here's our mutable variable, our mutable U32 that we're going to be aggregating into. We're going to initialize it as 0. And we're going to iterate over every element in the array. And that array is of length candidate count. And for each one, we're just grabbing the vote. We're going to square the vote. And we're going to add that onto the existing value of tokens spent. And then at the end, we're going to check that tokens spent is less than or equal to the budget. That's it. I mean, this is just one way of implementing it. There are other valid solutions to this. That's the one we've gone for.
I guess I can answer a couple questions though while he's out. So just specifically, I saw one of them. I made your same solution, but I'm getting an error for I in 0 to candidate count. The range of the loop must be known at compile time. I'm surprised that's the thing I mentioned earlier with how the array index must be known at compile time. But I'm surprised you're getting an error if you wrote the same exact code. I'm going to be posting the answers. I just posted it in the chat. This is for the example 2.1 that we just did. So you can copy this code if your snippet isn't working and you want to continue following along with the other sections, and I'll continue posting updates like for the new snippets once we get there. So if you have that error, Josh, you want to test out your audio real quick?
How's my sound now?
Perfect.
You're good.
Wonderful. Right. Hang on. Got to turn the questions filter on again.
So do you have simple debug tool like printline macro to trace the circuit? Not yet. We really want to add logging. This is something we do want to add. You can kind of debug using the constrain statement to determine like where something goes wrong in your circuit. But it's right now very manual in the developer to debug, and we do want logging. It's one of the main things. Internally, these U32s should be represented as field elements. Yeah, all our integers ultimately translate to our native data type. A U32 is just a field type with range constraints. And that's also why we're using, but we need those range constraints to enact some type of order for when we do comparison operations like greater than and less than. Will we get a plus equals operator soon? Don't know, maybe. Right now, no. I don't, you can mock it with, without, it's not a high priority because you don't have to use it to achieve the same functionality. I saw the loops end with semicolon. Why is it necessary? So we used, this is a kind of long story how we got here, but we used to support that you could aggregate the result of a for loop into an array, but we removed this functionality, but we were planning to add it back. Right now, we just added that, like literally like yesterday or something, that semicolons are no longer necessary. They're optional for for expressions. I don't know if the recently updated binary will yell at you for that, but in these examples, I believe we have semicolons behind all our for loops, but won't be necessary anymore. Is the vec macro not supported? No, we don't have we don't have those macros right now. The only macros we really have are the ones that tell you whether or not a function comes from the backend. And I'll answer this last question and then we can go to the next section. Does the main function always return nothing? Can it return a val, which can be a public output? Yes, you can return values from main. We just haven't yet, and in the examples I provided, main has not had any output, and the output has to be public. It's essentially treated like syntactic sugar as like you could think of it as like a public input as well. But you can return stuff from main, and I'll let Joss continue with the presentation.
Yeah, we're going to see that shortly, in fact. So moving on, we're going to jump over to the counterpart circuit. We're going to go over to the ballot manager circuit, who's going to count up these votes that we're producing on the other end. So we want to reveal the totals of all of the ballots summed together so that we know the result of the vote. We're going to be touching on some similar concepts again to do this. We're going to be aggregating again, so we're going to be using mutability, and we're going to be defining array lengths and globals, and we're going to be taking in votes as integers, so we'll be summing them as integers. And we're going to be dealing with a nested for loop. So at the moment, we can't currently do 2D arrays. So we're going to flatten our array of ballots, which is kind of like a 2D array. Each ballot has got 10 votes on it. So if you've got an array of ballots, then that's like a 2D array. But we're going to flatten it for our purposes until we do have support for that. But we're going to need to do a nested for loop to iterate over that flattened array. And then we're going to look at return statements as well. So this is what a nested loop looks like. Pretty much what you'd expect, one loop inside another. And you can see here's an example of some 2D array index arithmetic. Here is a return statement. So like in Rust, if you want to return something at the end of a function, you simply just don't have a semicolon at the end. So that final expression is what gets returned. Here's a function that returns 42, and then here's main, which is returning the value which is returned by getAnswer. And again, there's no semicolon here. Notice at this point, we have specified a return value for the main function. And as Maxime was saying earlier, it has to be public. So we do explicitly state that it is a public type. And when you come to run the Nago proof on this, if you leave the return property in the prover toml as blank, then Nago is going to infer that it should automatically generate it for you, and it will do that in the verifier toml. So here 2a, that's 42 in hexadecimal. So we're going to give you a couple of minutes again to mess about with those concepts. Again, you can look them up on the docs, and then we'll probably take more questions while you do that, and we'll return to the specification of the function that we want you to implement after that. We got somebody saying that they were able to compile their for expression without the semicolon, so that binary must be out.
Well, that's good then. So I guess not necessary to have the semicolon. You can still have it, but don't need it.
Question, would you mind explaining the contents of the toml files a bit more? So there are 3 toml files. There's the Nago toml, which is where you're going to state your dependencies for your program. In the case of this one, we're not using any external dependencies, so you won't need to touch that file. Then you've got prover.toml. This is where you can mock your inputs to the circuit. So you will write x equals whatever value, y equals whatever value, and return equals whatever value. If your public function, sorry, if your main function has a return, then the return property name is what gets matched to that. Then there's also a verifier toml. Once you've generated your proof, you will want to verify it. So inside your verifier toml, you are going to state properties again, but those properties are going to be whatever public inputs you have to your main function. What do we have to do for this task? Sorry, so the task hasn't started yet. We were just talking about the concepts you're going to have to use. So the returns, the nested loops, and using generating a return automatically. We're going to move on to the task now. So here's a spec. We're going to write a function, call it sumVotes, and that is going to take a 2D array of a flattened 2D array of elements of all the votes, and it's going to turn that into a 1D array of totals. So here's what our input variable is. It's notice that you can actually do arithmetic of globals inside the type declaration here. So if this is a voter count of 10, sorry, a voter count of, we're just going to do 2, Alice and Bob, but you could do whatever number in principle. It's just easier to test if we're doing 2 for now. Candidate count, we'll want it to be the same as we had in the other circuits, so we'll set that to 10. So global candidate count equals 10, global voter count equals 2, and they're going to get multiplied together, so the signature here is an array of U32 of length 20. And then our function is going to output our array of totaled votes, and that's going to be of length 10, the candidate count. So yes, important to note, we're now doing this in a counterpart circuit. We're not doing this in the cast ballot circuit anymore. So you'll want to go up a level and create a new Nago project. You can call it count votes, go into there, go into the main file, and start writing your function in there. We'll give you 7 minutes to try that out. It's 7 minutes too generous. How are we doing for time? We've got like 30 minutes left. Maybe we'll call that 5 minutes.
Actually, I think you have a bit more time.
Oh, yeah?
I think you have, I mean, our current trajectory is at 7 or like at 7 UTC. So in 50 minutes, we start the job fair.
Oh, okay. Right.
A little earlier, we have a few slides, but not too much. There are a few more questions in the Q&A right now. And also just a quick, did you answer the .toml file question, explaining the contents of that?
Yeah, so we talked about the 3 TOML types, Nargo, the verifier, and the prover.
Okay, so I hope it's okay if I mark that as answered. But yeah, there was 2 more. One is like, yeah, just not sure how to do.
What do we have to do for this task one? I think he asked that before we got to here.
Okay.
So that one should be answered. Maybe we can go back to the spec so people can have a look at it then, if so. But there's one more question I didn't understand very well. We need to recreate a project. Yeah, so the previous like circuit that we just wrote, that function check within budget, that's checking on the person who's voting side. They're submitting a ZK proof for that. But then there's going to be a separate circuit for the actual like ballot manager who manages these circuits. So it's going to have to be a separate project. So you're going to like CD out of that old project you made for the check votes within budget, and you're going to create a new one for the ballot manager. And that's where your sum votes method is going to live. If that's not clear, perhaps we can go through the infrastructure of the circuits once more. But essentially, you're going to have two separate entities here. How do I create a new array? I can type something in the chat, or yeah. If I do let x equals, oh, I see someone posted a reference to the project, but I would say hold off on that until we actually, unless you want to get a peek at the answers. But there's some good examples of how to declare stuff and other projects in the Nargo tests.
Is the input flattened in this way? Vote 1 1, vote 1 2, vote 2 1, vote 2 2. Yes, though it will be more than 2 votes per user. It'll be 10, so it'll be vote 1 1, vote 1 2, vote 1 3, vote 1 4, etc., until you get to vote 2. Or actually, it'll start with vote. We're indexing from 0, right? So vote 0 0, vote 0 1. But let's say that Alice got their commitment in first, and then Bob got their commitment in. So all of Alice's votes followed by all of Bob's votes. Maybe it's okay for us to share the gist of the prover input for the ballot manager, since that's not actually a solution.
You doing that, Joss, or should I grab the link?
If you beat me to it.
I got it right here. The
Cool.
prover toml for the manager.
Yep.
Yep, here.
Though notice in that prover, it's also got some extra ingredients that you don't need yet. You only need the votes, so you can comment out the other bits.
give it 2 more minutes, I guess.
Yep, I've got 2 on my timer. Does the silence mean that it's easy? Everyone's already done it? Or very hard? Question, do you need to allocate the output array? Sort of. You need to declare your mutable array your mutable array variable, and you'll probably use an array literal, and that's going to have a length in it. So you're sort of allocating the number of elements in that array then. I don't know if you'd think of it as allocate in the traditional sense, since memory management isn't really like a concern of Noir as far as I'm aware. What's the constraint here? There is none, actually. So there's an implicit constraint, which is the output of this program is consistent with what it's supposed to compute, but you don't have to use a constrain keyword.
Perhaps we should reveal the answer now.
Yeah, let's do that. So we've got our 2 globals, the candidate count, 10, the voter count, Alice and Bob, 2. Here's our function signature. It's going to take all of the votes. So that's our flattened 2D array, which is of size 20, which is those 2 globals multiplied together. We're going to output what is if you imagine that you had a matrix, you're just going to compress that matrix down to a vector. So that's going to be just the length candidate elements. Here is where we're allocating our array that we're going to aggregate into, the totals array. So we're just starting with every element in that array being 0, and it's of length candidate count. So we're using a semicolon here to denote that. And now to index over this flattened 2D array, we're going to iterate over rows and columns, I and j, and we're going to do some index arithmetic here with I multiplied by the candidate count, and then you add j. We're adding that onto whatever total is already in there. So it's kind of similar to how we were having to aggregate all of those squared votes before. We're not doing any squaring. What we're having to deal with is the indexing. So that's the puzzle in this one. And then at the end, we're returning the totals. Notice no semicolon. That's that method. And Maxime's going to post a gist to that snippet so that you can compile it yourself if you if you're behind, and that's also going to have the main function hooked up in it, so you could also prove on it if you wanted. All right, we've got another QA section, but we don't have anything in the QA yet. Is there anything in the chat?
I think we hit all the questions for this one.
All right, perhaps we'll move on then. We're going to go back to the user circuit now. We're going to be outputting the commitment of your ballot. So this is important because if we just state how many votes we're... How did I do that? Yeah, without outputting the commitments, we've got nothing to be held to later when it comes to counting the vote. And for producing this ballot commitment, we're going to need to use a hash function. Do you remember earlier we talked about, or maybe I'll just go back to the architecture slide. Not that one. This one, here we go. We have a ballot, it's got a secret, and when we want to produce a commitment, we're going to hash that secret with all of the votes in that ballot. This is how we make our commitment brute force attack resistant. Jump forward again. So the concepts we're going to need this time, we're going to be dealing with the field type. Up until now, we've been using integers, but the field we're going to need to use because of the interface on the hashing function. And in order to access that interface, we're going to have to cast our integers into fields. So we need casting. And to use this hashing function, we're going to need an import statement. The hash we're going to be using is Pedersen. You might be used to other hashing functions like Poseidon. I think we got a grant out for implementing Poseidon, but Pedersen is good enough for our purposes because we just need collision resistance. So this is an example of a field in use. So remember that a field is something that you're not going to come across in other traditional programming languages. It is specific to the realm of ZK programs because a field refers to the type that is used by the proving backend. Here's what it looks like to cast. So we start with an integer, and then we say that we want to treat this integer as a field. An integer already is a field, but now the program knows that it should be handling it as a field. And here's what it looks like if you wanted to cast your U8 into a U64. Here's what including the standard library namespace looks like. And here's that used in conjunction with the Pedersen hash. So it's part of the standard library, it's part of the hashing crate. It's going to take a transcript. So there'll be an array of fields here. And notice that we're only interested in the first element that gets returned by this method. The reason being is Pedersen is going to return an elliptic curve point, and we just want a single field element. So we're going to have an X and a Y. We're just going to use the X. That's sufficient. This is what the function signature looks like for the standard library Pedersen. You can check out the other standard library methods if you go to the Noir project in GitHub and go to the Noir standard library and source, and then hash.noir corresponds to the crate. There are all the other standard library crates sitting alongside it in that directory. But you notice that we've got this macro here, the foreign Pedersen. We're just saying that we're using an optimized gate, a custom gate from the proving backend in order to use this function. Oh, did I just give the answer there? I thought that was a hidden slide. No, okay, I was just confusing myself. We've touched on this already, but to recap, why don't we just use fields all the time? We've been using uints until now, and the reason is because we want to do that range check. You can't do the range check with regular fields. So in our earlier sample, we needed that range check. So have a go at importing the Pedersen. Have a go at doing some casting. We'll just give you a couple of minutes to mess about with that syntax and answer any questions. And then we'll go on to the actual task. So the task isn't set yet. We'll have the spec on the next slide. Can you give a prover TOML file? I guess you want the prover for, you asked that 5 minutes ago, so that would have been for the ballot manager. I think
I sent in the one for the manager, and then I also just sent the one for the user because they're about to do the user circuit again. So I just sent both of those prover TOMLs.
okay.
The return, someone asked, can the return be empty in TOML? Yes, it can. But right now, only for individual like integers or field elements, we actually, I think, like literally have a PR open that is just being reviewed to enable returning arrays. With an empty, you can autofill arrays in the verifier TOML as well. So that will be happening soon as well. You would just write return equals an empty string. One more question. I get expected 2 number of values, but got 4 number of values when trying to prove the ballot manager. So you're gonna have to comment out some of the value, probably some of the values in your prover TOML, because we haven't finished the manager circuit just yet. And there's some extra inputs there that are gonna be part of the next part of the workshop. You just need to match up the number of inputs in your main function and in your prover TOML.
All right, let's move on. Here's the spec for what we're going to write. Oh, and also this is now back in the user circuit. So we started in the user circuit, then we moved over to the manager circuit. Now we're moving back to the user circuit. So CD up, go back into cast ballot, and go to the main file in that. This function we're going to write is calculate ballot commitment. So that's going to take as input what we saw on the architecture slide earlier. So it's a secret followed by all of the votes. You can just put them all in an array together, and then that will be your input for the Pedersen function. So the input to this function we're writing is all of the votes. So that's the candidate count length again. And then also this secret. And then you output the field, which is going to be the x coordinate of the Pedersen. So the challenge here is forming the array, which is the transcript, which is going to be the secret followed by all the votes, and then passing that into the Pedersen hash. We'll give you 7 minutes to try that out.
One more question we have is Nargo compile not yet implemented in the Linux binary version? The Nargo binary should be feature complete. Perhaps there's some unique architecture edge case that's messing with that. Please hop in our Discord or something after this if you're having issues still with the binary. We would like to make sure you don't have those issues. No, I'm not sure why that might be going wrong, and a bug report would give us a lot more info. It should be working though, and you can also try compiling from source if the binary isn't working for you, and it should work on Linux with the WASM backend. Yeah. Is there support for big int in Noir? So good question. Not yet. We actually do have a grantee working on a big int implementation, like written in Noir itself, and that should hopefully be not far away. But there is we are in discussion about putting big int directly into the compiler as well, because we think it's would be much more efficient, that we can make it much more efficient that way. But that's just it's something that we definitely really want. Yeah, and there should hopefully be a Noir implementation soon. And then someone asked, can you go back to the spec? Joss already got it and he's put it up.
Just a quick reminder to folks, just be sure to put your questions in the Q&A, right? Sometimes I see them a little bit in the sessions chat.
Right, I see that now. Could you guys reveal just how to import the function to do the hashing? Yeah, sorry, I'll go back to that slide. It was here. So we're using the standard library main namespace. It's going to be standard library : the hash crate : and the method.
Yeah, and you might see that dep keyword. That essentially means it's an external dependency. But like that's because the standard library we automatically incorporate into Noir. You're not going to see that in the Nargo toml. That's why your Nargo toml doesn't have any dependencies. For example, when I earlier showed like if I have like utils equals some like local path in my dependencies, I would also have like use dep : utils, and then I can use functions in that from that import. So we're doing the same thing here. We just automatically are incorporating it.
I know when I get to this part of the code, when I've used this, my most common typo is to use a single colon instead of a double. You can get thrown off by that compiler error. One more minute. Would it be possible for someone to run a version of cast ballot that ignored the token budget? I.e., does the system mean that the count votes role is verifying that the budget was respected? So when you come to counting the votes, you don't need to check that the budget was respected, because when the user cast their ballot in the first place, they would have produced a ZKP which stated that they'd respected the budget. And then that commitment and proof would have gone to a smart contract, and that smart contract would have verified that proof and said, yes, this voter here has respected the budget. And so when the ballot manager comes to aggregating all these votes together, it just knows this is a valid ballot. It's okay because the smart contract has already verified it, or the ballot manager could verify it themselves. Is there neo-vim syntax for star.noir? I don't actually know anything about neo-vim.
We have VS like a preliminary VS Code syntax highlighting that you can install from the VS Code marketplace. I've actually never used NeoVim. I'm sure it'd be easy to port that over, but right now we don't have I don't think so for NeoVim. And what about a formatter is another question. We don't have a formatter. It would be great to have Nargo FMT. Would make things really nice. This is some of the things that we will add as we've been heads down writing the language. Now we can start adding a lot more tooling, and that will be hopefully a part of it.
All right, I'm going to move on now. Here's our solution. So we're importing that namespace. Here's our function signature. We're calculating the ballot commitment using a secret, which is a field, and then the votes. And then we've got to form this transcript. The transcript is going to be the length of all the votes plus a secret. So we've got a length of +1 here. And it doesn't really matter what value you initialize it to, because we're going to assign all of them. We assign the 0th element as the secret, and we're going to iterate over the remaining votes and do that index +1, assign it, and we're going to cast it to a field as we go, because the Pedersen hash requires that we input an array of fields. And we are returning the x coordinate of the elliptic curve point that comes back from the Pedersen. Again, no semicolon, because this is a return. You see, we've got this field being returned in the function signature. And I think Maxime is going to share a gist of that if he hasn't already. In fact, that will now be the complete user circuit. So that gist will also will also show how to hook it up to main. Have we got any more questions at this point? Do you plan to support exporting to Cairo?
That would be extremely challenging, if not impossible. Cairo is very specific to StarkNet, and they do have like hints that enable private inputs or something. I need to look a little bit more, but Cairo, I don't think you can have basically like this hidden data like we do in Noir. You could theoretically have for a verifier. Oh, that would be neat. But it's not something that we've been able to allocate resources towards. But if someone wants to write a Cairo verifier for TurboPlunk, that would work with Noir. And then as we upgrade our proving systems, if someone continues to also upgrade Solidity verifier to also be a Cairo verifier, that would be great. That would be, now you could export Noir programs to StarkNet. One more question here. Transcripts inner type is inferred as a field. Here, do you know what that question means, Joss? Sorry.
Okay. Yeah, I think I get it. So
from there. Okay.
what have I said? Yes, so we've only called it 0, right? We haven't specified a type. So I guess at this point it's a polymorphic integer. Is that right, Maxime?
Yeah, so when you don't specify a type, it's going to be a polymorphic int, and then the first place it's used, that's going to be the int type. So here, the first place we use transcript 0, we're labeling it secret. So it's gonna infer that transcript is a array of fields. So actually, a good question. I wasn't sure what he meant by transcript, but
cool. No questions, so I think we'll move on. All right, we're jumping back over to the counterpart again, back to the ballot manager. So we've now got the user circuit producing these commitments. They're going to the smart contract or whatever consensus system we're using. And now the ballot manager wants to take all of those commitments and check that they're valid. We're not covering any new concepts at the moment. We're just going to combine everything that we've learned up until now. We will be needing to recalculate all of the commitments for all of the ballots which are being inputted into the manager's circuit. So remember, we've got that flattened 2D array of votes. So it'll be Alice's votes followed by Bob's votes. So we're going to have to take that chunk of votes and then combine it with a secret. You can see here are our inputs. We've got an array of secrets. These arrays are all going to have to follow the same order. So this array of 2 elements is going to be Alice's secret followed by Bob's secret. This array of commitments is going to be Alice's commitment followed by Bob's commitment. And then all of these votes is going to be Alice's votes followed by Bob's votes. So that's the task. And of course, you're going to have to do a constrain in here. You can actually do a constrain on all of the hashes as you calculate them. So go back over to the ballot manager circuit and have a go at filling out this function, check commitments. We'll give you 7 minutes for that. This is the last exercise, by the way. If you made it this far, well done. Should we reuse calculate ballot commitment from the other file? So you can try and do this, but you're going to run into some challenges. You'll probably find yourself rewriting that function because of this flattened 2D array of commitments. It is possible to get something that looks close to that function, but you're going to need to add an extra parameter, which would be like an offset inside this 2D array where you want to inspect. And then if you do that, you're going to have to get into some other advanced concepts like compile time arguments. So if you want a challenge, you can try doing it that way, but I'd recommend re-implementing it, using a nested for loop. Is there not a way to use the array as a pointer and just shift it? So I think
this kind of relates to the old question about references. We don't have arrays are technically like a pointer underneath, but once again, we don't support this non-determinism with arrays, and yeah, not right now. It's a bit more adding that to a ZK circuit language adds a lot of complexity, and it's something, it can be very powerful. We want to add it, but it does not exist right now. You have to set your arrays so that they're known at compile time.
Got another 4 minutes. Question. Earlier you mentioned you did not support early return. Is this by design or something which may be supported later? Oh, I have no idea about that one. Maxime?
Yeah, so you can kind of mock early return through other means. So we haven't necessarily we just haven't added it. You can only return at the end of the last statement of a function right now. It may be supported later, but it kind of requires you're almost like short circuiting, and that's something that it's just we haven't prioritized just yet.
We'll give you 1 more minute. All right, that's 7 minutes. Moving on. Here's a solution. or our solution anyway. So you're importing that namespace again. We've got our two globals. We already had those before. To check the commitments, we're going to need all the inputs, which are the commitments, the secrets, and that flattened 2D array. We're iterating over every voter, so Alice and Bob, and in each case, we're going to have to reform their transcript. So again, that's going to be an array length of 11, 10 plus 1. And we set the first element as a secret according to the order of the voters. So this will be Alice's secret first, and then on the next iteration, that'll be Bob's secret. And then we've got to do the same business of copying in all of the votes and casting them to fields, but this time we're doing it with some 2D array index arithmetic. And then at the end, we're going to constrain whatever input commitment is at that position in the array to the output of the Pedersen hash, or specifically the x coordinate of it. Notice that we're performing this constraint inside of the for loop. You could, if you wanted, have another mutable variable which you set a Boolean on if any one of them wasn't correctly matching the Pedersen, and then you could just constrain it at the end. Either way is valid. So, any questions? Oh yeah, Maxime, did you post that in the gist? Cool, thank you.
I also just posted the circuit inputs once more, so you don't have to scroll up.
Sweet. So at this point, we've got two complete circuits. So you can try running the prover and the verifier on them. You'll notice that the sample inputs for the user circuit has got the inputs for one of the voters commented out. I can't remember if it's Alice or Bob, but you can just switch the commenting out around and then rerun it. And then you'll notice in your verifier, Tommel, that you'll see the commitment being outputted. And if you look back over at the user manager inputs, those are the commitments that got copied in the output in that verifier, Tommel. And the user manager inputs is going to contain the complete set of inputs to say that I have got a valid summation of all the votes. And then that would get posted on chain, it would get verified, and so concludes the election. We got any questions? Is there a way to get more information about the line that caused the issue in an error? I get index out of bounds. The length is 20, but the index is 20.
So you're probably indexing incorrectly, as it sounds like an indexing error, and the size of the all votes array should be 20. So you might be just somewhere the index is off. Perhaps your transcript array needs to be, well, it's actually length is 20 and the index is 20, so it's probably related to your all votes array there.
But to answer your question as to whether you can get a line number, I think at the moment you can't do that.
Yeah, we have to add a bit more around, I guess, some of the error handling, specifically when evaluating the program. We have some pretty good error handling with regards to compilation and building, but this is part of our tooling improvements that need to be done.
Cool. Well, I guess we're nearly at time and I can't see more questions. So this might be where oh, sorry. Yeah, you might have seen it in the gists, but in case you hadn't seen it in the gists, this is what it looks like when you assemble it all into the main function. So this is the user circuit. So you're going to do the constraint check. You don't care about the return because the constraint check is happening inside that method. And the calculate commitment, you do care about the return. So notice a lack of semicolon. And notice that we got this public field being outputted. Here are those TOML files we were talking about. So in goes the inputs, out comes the commitment here. Inputs, here's commitment, and then we copied that. Oh, and then we assembled the main function for the manager circuit. So we're checking all the commitments, and then we're outputting all the summed votes. And that's what the inputs look like here. If you're in the near future, when you execute this yourself, you won't need to specify the return, but I think with the current build that's out, you do need to, because it's an array of returned integers. It doesn't know how to auto-generate that just yet. The fix is on its way out. And if you want to see the complete example, you can go here. Contains everything you've just seen. I think, sorry, there were a couple of slides for Maxime to finish on.
Sure.
These ones will be fast though. We do support generation of a Solidity contract based off of our like your Noir circuit, and this enables a lot more powerful use cases. So you don't have to you can actually have verification in the smart contract rather than in just like an individual verifying a circuit. And this can combine, it enables autonomous execution based off of your ZK proofs. Actually, I'm noticing someone asked a question, how do you get the user's commitment? We're assuming in this case that the users are sending it to the ballot manager, who's then using those commitments. But for example, if we had a contract where the user was verifying their circuit, the ballot manager could fetch the commitments from that smart contract and also see that these votes, the budgets are valid and the users have submitted valid ZK proofs. You could go to the next slide, Joss. And then in order to easily interact with these circuits and the Solidity contracts, we also have TypeScript wrappers. This is one of the main places, though, that we are going to be working on tooling in the coming months, and you can expect lots of improvements and hopefully improvements for the developer experience so you can easily have Noir circuits that are interacting with Solidity contracts, or just in TypeScript if you prefer developing that way. And here's a bunch of the resources that might be relevant to you based off of from this presentation. Please join our Discord as well if you have any questions or errors while you're maybe programming. Yeah, I hope everyone enjoyed the presentation.